All right, folks, just a reminder, if I could please have your video enabled. Thank you. Appreciate it. All right, we'll get started here. It's 9:30. All right, Coden, if you could enable your video too, please. Thank you. All right. So phase diagrams, we'll start on this today. I think the best way to handle phase diagrams is to really just give you an example and just show you how we use them. So this is the phase diagram for water that we're looking at here. And as you can see, we have pressure on the y-axis, we have temperature on the x-axis. And then over here we have different phases, S for solid, L for liquid, G for gas. I'm sure you're familiar with those kinds of abbreviations. The lines represent places where we can see phases that are in equilibrium with each other. So for example, along this line here, we'll have solid and liquid in equilibrium with each other. In other words, we'll see both at these particular temperature and pressure values. And then over here, we'll see liquid and gas, and down here we'll see solid and gas in equilibrium with each other. So these lines represent sort of separation points between the phases, if you will. Now, a couple of other things that we can do here is we can determine what phases are present at a given temperature and pressure. And the other things we can do are determining the triple point and the critical point in this kind of diagram. So this is water, as I said here. And one interesting thing about water is the slope of this solid liquid line that you see here. In most substances, what we see is a solid liquid line that goes in a more positive direction, more like this, where my cursor is pointing up towards the right rather than the left. The reason for this is because of the density of, no, not the density of water, the density of the solid relative to the liquid. One thing we know about ice is that when we stick it into water, it floats. And the reason for that is because the solid is less dense than the liquid. This is not actually a very common situation. In most substances, the solid is usually far more dense than the liquid is. I mean, it makes sense. For most things, the solid phase will tend to sink into the liquid. But could you imagine what would happen if ice sunk in liquid? There wouldn't be icebergs. We wouldn't be the way, the Earth wouldn't be the way it was if that were the case. But what that means is that as pressure increases on the liquid, pressure increases on a solid, it's kind of more likely to turn into a liquid. And that's kind of weird. That's not normal. I mean, it's the reason that people can skate on ice is because you put pressure on the solid, it turns into a liquid. And that liquid barrier allows the skater to skate on the ice. Or, hydroplane if you're in a car, for example. So all of that is caused by the fact that the solid phase is less dense than the liquid phase, which is kind of weird, which leads to this sloping line that slopes in a negative direction rather than in a positive one. So let's answer some questions about the phase diagram and we'll see how we do that. What phases are present at 200 degrees Celsius and 100 atmospheres? So all you have to do is just look down the bottom for 200 degrees Celsius and then 100 atmospheres, and you'll see that comes out to be liquid. So you just need to find the phase present at that particular point. Does anybody have any questions so far? What phases are present at point X? Well, point X is over here on the liquid gas line. So it would have the equilibrium between liquid and gas. So if you were looking at something that had that temperature and that pressure, that's what you would see. You'd see a mixture of liquid and gas in the container. The triple point is where all three phases are in equilibrium with each other at the same time. And this is where the two lines join together. Solid, liquid, gas, all will be present at the same time at this particular pressure and temperature value. Does anybody have any questions so far? All right, so for the first 3 questions, I'm just going to do a poll here. How do you feel so far about the first 3 questions? 5, 4, 3, 2, 1, 0. Yeah, more people understand halfway than I thought. Can I get some questions here, please? Any questions? If you don't ask questions, then I don't know how you're going to end up getting a better understanding of what I'm talking about here. All right. The next thing is the value of the critical pressure. Now, the critical point is the end of the liquid gas line. It's right here where I'm putting the cursor. So you might think, well, that line is just going to continue up, right? No, actually, that's where it ends. That is where the line ends. The line doesn't go any further than that. That is the critical point. So what is the critical point? Well, it's the point at which, after which, no matter what pressure you put on the particular substance, you can never get it back into the liquid phase. So what I'm saying here is, let's say the temperature was, say, 400 degrees Celsius. So that's after the critical point here. What that means is the temperature is so high that no matter what pressure we put on it, we cannot turn it back into a liquid. That's what the nature of the critical point is. So there's 2 things associated with the critical point. We've got a critical temperature and we've got a critical pressure. So the pressure is 218 and there's 218 atmospheres, and the temperature is 374 degrees. So that would be the end of the liquid gas line. Okay, somebody had a question here. Let me check on it. Can anyone see the professor's screen? Well, yeah, that's a good question. Samia, I'm not sure why you can't. I am sharing it.
Yeah, I can see it.
Okay, thank you. Yeah, I don't know. Maybe you'll have to leave and come back. That would be my suggestion. But please come back.
So the critical temperature is the point where it'll never become a solid again. It's so.
Could you repeat that, please?
Sorry, for what you've just said for critical temperature is it's the temperature where it's so hot that it will never become solid no matter what pressure.
Liquid.
Never become liquid. Okay,
yeah,
thank you.
Yeah, because it'll be a gas at that point, and you can't get it. Well, if it can't become a liquid, it can never become a solid either at that temperature. So, you know, the thing is that if you've got a gas, if you put pressure on it, you should be able to theoretically squeeze that gas so hard that it turns into a liquid, right? That would be the supposition. But the reality is that once the temperature gets too high, they're moving so fast that they can never settle into that liquid phase. So that's the nature of the critical point. Is that okay, Joseph?
Yes, thank you.
Okay. Let me see. How do you feel about the critical point? How do you feel about the critical point? Five, 4, 3, 2, 1. Okay, that's good. I'm kind of surprised by that. More people are okay with the critical point than they are the first 3 questions here. All right, the last one here, this is kind of the hardest of them, but it's really not that bad either. The temperature is held at 25 degrees Celsius. Describe in detail the phase changes that occur as the pressure is increased from 0.0040 atmospheres. The answer to that is first it's a gas and then it becomes a liquid. So how do we deal with that? Well, in this kind of question, what we're actually doing is we could be starting at a certain pressure and then moving that pressure up, but that temperature is going to remain stable. So in other words, the line is going to be completely vertical. It could go in either direction, by the way. It could be decreasing or increasing on the pressure. The other possibility is to have a pressure that's constant, and increase or decrease the temperature. So those are the two possible ways that we can handle this problem. In this instance, though, we're starting at 0.0040 atmospheres, which is down here. We're at 25 degrees Celsius. And what we're doing is we're holding the temperature at that same 25 degrees Celsius and increasing the pressure. And you can see that pressure is increased from 0.0040 atmospheres. As you can see, the starting point is in the gas phase. And then as we increase the pressure, it goes from gas into a liquid, which kind of makes sense. I mean, if you're holding the temperature at the same temperature, and we're not past the critical point, it's natural to assume that what's going to happen is it's going to start as a gas, and then eventually it's going to turn into a liquid because the pressure gets too high. Does anybody have any questions? Now, if the solid liquid phase line was going the opposite direction, eventually it would also turn into a solid as well. But remember, with water, it's a little bit different because the solid is less dense than the liquid, which is why it won't become a solid. All right, let's see how you feel about question E. How do you feel about question E? 1, 5, 4, 3, 2, 1. I like that. It's good. Everybody understands it. I like it. Okay, let's take a look at how this looks on the practice test. I'm going to open up another instance of my courses as well while I'm at it, but we'll see where that just goes in a second. Okay, so phase diagrams. And what you'll be doing here is, you see this is a different kind of phase diagram than the one we were looking at. This is the one for carbon dioxide. And as you can see, if you look at the solid liquid phase line, it's interesting. It does go in that opposite direction that I was talking about. So the solid is more dense than the liquid. So if you had liquid carbon dioxide, the solid would actually sink. It's not like water where the ice floats. So the first question here is the critical temperature. So the critical temperature is the end of the liquid gas phase line, and you'll see it's going to be about 300. Well, I actually don't have units on that. I should have units. It'd be 300 Kelvin would be the answer to that one. All right, consider the phase diagram below. There's your temperature there. So this is for water. And let's see, it says the pressure closest to the triple point. So the triple point is here, and the pressure closest to it would be 10 to the 3 pascals. Does anybody have any questions so far? Okay. What phase is present at point X? It'd be solid and liquid. So whatever's on that line. Any questions about that one? Okay. What phase is present at 100,000 pascals and 300 K? So take it to 300 K, and what would this be? This would be 1,000,000 pascals, actually, 10 to the 6th. So it's 300 and then 10 to the 6th, and it would be the liquid phase. Anybody got any questions?
So for critical point, sorry, I know we're just past that.
But it's right here. It's the end of the liquid gas line all the time.
Okay, okay, thank you.
So if you were asked for the pressure, it'd be about 10 to the 7th. If you're asked for the temperature, it'd be about 600 K.
Got it, thank you.
So this one, the temperature is decreased slowly from 300 K at 10 to the 4th pascals. Okay, so what you do is you start at 300 K here, and it's decreased from 10 to the 4th pascals. So 10 to the 4th pascals is here, and we're decreasing it. So it starts as the gas, and well, and then it starts as a gas, and we're decreasing the temperature. Okay, so the temperature is going to go down, so it's going to go from a gas and turn into a solid, and that would be the answer here. So all the possible answers are here, but yeah, it starts as a gas, turns into a solid. Any questions? All right. How do you feel about the test questions I've just discussed? 5, 4, 3, 2, 1. There we go. That's good. Not too bad. Any questions? Any questions? Okay. All right. We're going to now look at intermolecular forces, and for this, I'm going to pull up a video here. Change the share as well. And let's see. Actually, let me see if I can find the link here. Animation. Solid, liquid, gas. Let's see if I can find the one that I like to use. I'll try one more thing. Oh, this is the one. Yeah, I like this one. I think I'll add this in as a link as well. Let's have a look. So let's talk about states here first. So this is a representation of what we see for solid. So solid represents all of these. I like this because you can see it's actually kind of realistic, because at the solid state, nothing is stopped. I mean, if you were to cool it down to 0 Kelvin, theoretically it would stop. I don't know if I can cool it down to 0 Kelvin. See, it slows right down. Oh, yes. Probably won't let me go lower than 1K. But you can see that these things aren't moving very much at 1 Kelvin. At 0 Kelvin, theoretically, they'd stop. All right, but we can heat this. See, a little fire comes up. Whoa, look at that. Okay. So I'm going to heat it. And you can see what happens is that, all right. So at this temperature, we're getting more of what I would consider to be a liquid phase. And the liquid phase, you'll notice everything's pretty much, there are some in the gas phase, I will admit, but most of them are in the liquid phase, which means they're kind of touching, right? Or at least possibly touching. And then that would mean that they're liquid. So what I'm going to do is I'm going to heat this right up now. We'll see what happens. Okay, now look what happens. Now these molecules are all in the gas phase. Now by the gas phase, what I mean is they're not permanently touching each other. So that's a real difference between the liquid and the gas phase. Now, in order for that to happen, the reason that liquids turn into gases is because energy is added to the liquid so that the molecules can no longer touch each other. So what that presupposes is there must be some sort of force when it's in the liquid phase that keeps it from turning into a gas, all automatically. And that is what we're calling intermolecular forces. So in summary, what I'm saying is, in the gas phase, the intermolecular forces have been overcome. So I'm going to cool this back down and it will turn back into a liquid. And then there won't be the temperature present to allow these molecules. See, look at that. There we go. That's more, I think that might be a little bit too close to solid, but let's see if we can get in liquid phase again. There we go. Now, maybe a little bit harder. Okay, now that's more liquidy there. So now the molecules move around a lot more, but they tend to touch each other a bit more. And that's because there's forces between them, attractive forces that are sort of keeping them close to each other. It's only the temperature that allows these molecules to overcome those forces. All right. So tell me about your understanding of intermolecular forces in relation to liquids and gases. That's really the point I'm trying to get across here. 5, 4, 3, 2, 1. That's good. All right. So anybody have any questions? Good. Okay, so let's talk now about what kinds of intermolecular forces will allow us to figure out what it is that's keeping these molecules touching each other when they're in liquid phase. Now, before we do that, we do need to introduce you here to some structure expression, especially for carbon compounds. And what I'm really focusing on here are line structures. So these are not line structures. These are some of the different ways we can express carbon compounds. I'm not really going to go into them, but what I will go into is the line structure. And a line structure is representative of carbons and hydrogens. When there's nothing else there, that's all you're seeing. So if you're seeing lines like this, what we're actually looking at is each point in that line structure representing a carbon atom. Now, carbon has 4 bonds usually. So what that means is that if you're seeing just those points, then you have enough hydrogens on that carbon in order to make it up to 4 bonds. So here's what I'm talking about. Let me point my cursor here at this carbon right here in the middle. Visibly, you can see there are 3 bonds to other carbon atoms. What that means is there must be 1 hydrogen on that carbon. Likewise here, this carbon has 2 bonds, which means there must be 2 hydrogens on it. This carbon actually has 4 bonds, so there are no hydrogens on it. And this carbon has 1 bond visible, so it must have 3 hydrogens on it. Does anybody have any questions? How do you feel about line structures so far? Five, 4, 3, 2, 1. Okay. All right. Any questions then? I mean, so some of you halfway understand it, so I need to get some questions here about line structures. The reason we use them is because they're easier. I mean, it's much easier to write out these line structures than to go ahead and write the carbons out with all the hydrogens connected to them. But the whole point is, or the rationale is, that carbon has 4 bonds generally, and any bond differences that you see must be hydrogens if you can't see the bonds. Okay. When there are heteroatoms in place, and heteroatoms are things like oxygen, nitrogen, fluorine, chlorine, anything that isn't carbon, basically, or hydrogen, then we still express them as part of the line structure. And as customarily, we generally do show the hydrogens on these heteroatoms. So if you saw a structure like this with the carbons here, it would translate to this structure here with the OH coming off the second carbon in the chain. The bottom line, though, is that whenever you see just these lines, you've always just got to consider them to be carbons and hydrogens. That's all I'm really trying to get you to do. Whenever you see straight lines like this, just consider them to be carbons and hydrogens. Anything connected to them that isn't carbon or hydrogen is just read as what it is, O, N, Cl, Br, whatever it happens to be. Does anybody have any questions? Yeah, I'm sensitive to this because I did see that there were 12 people who understood, but 6 people who halfway understood.
The hydrogens, are they usually H2 with the carbons?
Well, it depends. I mean, like this carbon, this is a carbon here on the end, Olivia, and there's only one bond that I can see there, which means there must be 3 hydrogens on that carbon. So it's always enough to make it up to 4 bonds.
Yeah, I just like so used to seeing it with just lines to each hydrogen or each element. So it's
Right, I know it's something a little bit new, but you know it is easier once you start expressing it that way, because then you don't have to write out everything.
okay.
Okay, so my main thing here, just if you see just lines, just think of them as C's and H's. Okay, that's all. Don't worry so much about how many H's there actually are. It's not really that important. I just want you to see there's just C's and H's. Except for here, obviously, where there's no H. Okay. Any other questions? Yeah, I think the main concerns people are having is maybe just with how many hydrogens there are on each carbon, but you actually don't have to worry about that. It's not something I'm trying to get you to do. I just want you to see, I mean, you think I'm making this up, but no, I'm not. This is how structures are expressed by a lot of people in the scientific community. And the reason for that is because it's easier, it's more convenient. And I think it's useful for you to look at this. If you don't believe me, next time you open a any pharmaceutical packet, and you open up the leaflet that you'll find in there, usually it's a small square, and then you fold it out, then you'll see the structures of the compounds that are in that pharmaceutical, and they will be expressed in this manner. They don't show all the carbons and hydrogens. Okay, so let's look at the actual intermolecular forces we're going to discuss. The first one is going to be called the van der Waal. The second one is called Dipole Dipole, and the third one is called hydrogen bonding. So these are the 3 intermolecular forces we're trying to discuss. Now, if you remember what the intermolecular forces are and what they're responsible for, they're responsible for keeping these molecules in the liquid phase, keeping them touching. They're the attractive forces between these molecules. Now, as such, these attractive forces have differences in their strengths. The first one we're talking about is called van der Waal. This is the weakest intermolecular force. And this is the only intermolecular force we see in hydrocarbons. So what are hydrocarbons? Well, it won't surprise you to learn that hydrocarbons are compounds that contain hydrogen and carbon. Okay. What this results from is what's called a temporary dipole. So what is a temporary dipole? We've talked about dipoles before in the context of the VSEPR theory, but we're going to discuss them here in a little bit more general context with regard to intermolecular forces. So let's look at, let me see if I can I'm going to pull up an animation here. And I've got one in one of my mini lectures, the Intermolecular Forces main concepts, this one.
This mini lecture is about phase. This is to have an
Let me see. No, that is not the right.
Compounds that have AC.
That is not the right one. I wonder if I got the two mixed up. That would be annoying if that's happened. Let me go back to
Of my discussion about intermolecular forces, and what this will do is give some examples and relate.
No, let me go back to the other one then. It does seem to be different.
This mini lecture is about what kind of, you might be able to get a little bit of this. All the molecules.
That was weird.
The weakest of the.
Let's see if we can just, that was weird that it pulled up a different video. Okay. So this here is
really.
So this is a diagram here. I'm showing you this animation here of it's a little bit hard to see, but what we're looking at is electron movement from one side of the molecule to the other, which is causing this
nice
temporary dipole
interpretation of van der Waals forces. You can see what's going on is the electrons are moving from one side to the other. It's a very temporary type situation on the dipole.
All right, so there's a temporary situation going on here with the dipole. So what I'm looking at here is, you can see I've got the electron cloud here representing the CH bonds, and what I'm showing you in that other diagram is an animation where the electrons can move from one side to the other. And this creates a very temporary dipole, temporary situation. And what can happen is then these molecules can kind of join together in a chain where the negative and the positive are kind of attracted to each other. So this is what creates a van der Waals force. And this is the force for hydrocarbons that keeps them in the liquid phase. But it's a very, very weak force because the dipole is only temporary, right? The dipole is only temporary. Now, I'm not going to do a poll on this one yet. Well, I'll do all three, and then I'll see where people are at with their understanding. Does anybody have any questions so far, though? Okay. Now, the intermolecular force that's next is called dipole-dipole, and this results from a permanent dipole. So these tend to be 10 times stronger than the van der Waals forces we were just looking at, because now instead of having a temporary dipole, we've got a permanent one. Now, van der Waals was the force that we have with hydrocarbons, where there's only C's and H's. But now if we throw in some other atoms, heteroatoms, especially nonmetals we're talking about here, then what we're going to see is CX bonds being formed. And the X can be pretty much nitrogen, oxygen, sulfur, or any halogen, which would be chlorine, bromine, iodine, and this will, or fluorine, and this will introduce what we call a permanent dipole. And this permanent dipole interacts in the same way as a temporary one does, but since they're permanent, this is a lot stronger. This is a much stronger situation. So I'm going to show you this in the video as well.
An animation of that as well. You can see this here. Because these dipoles are permanent, you can see how they might be inclined to line up from positive to negative and engage in activities that will keep these molecules pretty much stuck together.
Right, so more stuck together than they would be if it was van der Waals forces that we're talking about here. Does anybody have any questions so far? Okay. The last one, and this is the very much strongest of all the forces that we're talking about here with the intermolecular forces, we have the hydrogen bonding, which is really a special case of dipole-dipole, and it's 10 times dipole-dipole. Specifically, it is OH, NH, and FH. Now, what makes these so special is the fact that the O, N, and the F are the three most electronegative elements on the periodic table, and they're all connected to hydrogens. Now, from a diagrammatic point of view, what that means is we have very strong dipoles between these elements. So if we take O, for example, and the H, O is a pretty big atom compared to hydrogen. So that's the O, and this is H. Now, because H is so small, what it means is when we get those attractive forces occurring, where that's delta minus, the hydrogen's delta plus, then this distance here, this distance here becomes quite short because the hydrogen's so small. And because that distance is shorter, it means the attraction, the electrostatic attraction between the positive and the negative is much stronger than it would normally be between other atoms. So because of that, then we get a much stronger intermolecular force occurring. Now, I'm not a real fan of the name of this. I think hydrogen bonding is an awful name for this particular intermolecular force, but this is what we're stuck with. It's the same force, if you've done any biology, that keeps DNA strands in the double helix. It's hydrogen bonding between the base pairs in DNA that allow them to stick together the way that they do. So it's actually quite interesting how that was discovered by Watson and Crick. The nature of what is holding the base pairs together. Does anybody have any questions so far about this? Okay, so let me give you a summary here of what's going on with the intermolecular forces that will allow you to be able to look at compounds and be able to determine what the main intermolecular force is going to be. So with CH compounds, and there I'll just put lines like this, it's going to be van der Waals forces, VDW. With CX compounds, whoops. Then we're looking at dipole-dipole. Now remember, X is a non-metal. That isn't carbon, right? Or hydrogen. X does not equal C or H. And the last one, containing OH, NH, FH, these are all considered hydrogen bonding. Now the strength, or the relative strength, it will be hydrogen bonding is greater than dipole-dipole is greater than van der Waals. All right, I'm going to do a poll here. I'm not expecting great results because I'm only sort of halfway through here and you haven't seen how the questions are going to be on the test yet either. So let's talk about just your level of understanding so far. Looks like somebody was 1.5 ways, but your reiteration of being okay. Thanks, thanks, Mikhail. All right, let's see where we're at. What's your level of understanding so far? I'm not expecting people to understand this completely at this point. Okay, 5, 4, 3, 2, 1. This is kind of what I was expecting at this point. I'm really glad there's no I don't understand at all, so that's good. But the fact that that all of you either understand it at least halfway is good. Is good so far. Don't be upset at this point, right? I mean, we need to continue with this, and I need to give you a bit more context, give you some examples. Does anybody have any questions at this point? Okay. All right, I'm going to continue with this so that I can show you the examples, and then we can, and then you'll get a better idea of what's going on. Okay. The other things that also affect intermolecular forces are going to be the chain length and branching of the chain. So let's talk first of all about chain length. That's probably the easiest one to talk about. If you've got a carbon chain that's long versus one that's short, I think it's pretty easy to see that when you've got the long chain carbon, there's more opportunities for surface contact because the chain is longer. And by surface contact, I'm just talking about between the chains themselves. So look at these bubbles that I've got around each of these carbon chains. What I'm saying is the longer the chain, the bigger the bubble, or the longer the bubble, the more opportunities for those carbon chains to interact. So what that means is that a longer chain will generally mean there's more intermolecular forces between those chains. Does anybody have any questions so far? Now, branching is a little bit harder to explain, but branching is a situation where we have carbons coming off the main chain. In those instances, instead of the shape of the molecule being sort of like a cigar, it becomes more like a sphere. So what happens is that affects the way that the molecules can pack together. So here's what I want you to imagine. When you've got a bunch of straight chains, what you're looking at is what I would consider to be like cigars in a box. There's a lot of surface contact between cigars in a box. However, when you have carbons coming off the main chain, what we've got then is something a little bit different. It's more like spheres in a box. And as you can imagine, putting a bunch of spheres in a box is going to create less surface contact. The less surface contact there is, the less intermolecular forces there are going to be as well. All right, let's see how people feel just about chain length and branching. Okay, chain length and branching. That's all I want you to focus on right now. Chain length and branching. 5, 4, 3, 2, 1, 0. Okay. That's kind of what I expected. Does anybody have any questions? Does anybody have any questions about chain length and branching at this point? Okay. All right, so now we can sort of tie all this up in a bow. We can see exactly how we can use these intermolecular forces to do problems. And the first thing that we need to be aware of is what boiling point is. Boiling point is the temperature required to turn a liquid into a gas. So when you're boiling water, that's what you're doing. You're turning the liquid into steam, liquid water into gaseous water, which is steam. In the liquid phase, we have molecules touching. In the gas phase, the molecules aren't touching. It's the intermolecular forces that keep the molecules touching, and the link then between intermolecular force and boiling point is that the stronger the intermolecular force is, the higher the boiling point will be. I'll say that again. The stronger the intermolecular forces between the molecules, the higher the boiling point is going to be. Does anybody have any questions about any of that? Okay. Let's look at some examples of alkane boiling points so that you can see some of this in action. And actually, let me see if it's Michigan State. Here we are. Okay. Yeah, I like this one here. So take a look at the different compounds that we have here. Now, here's how I want you to interpret it. We've got pentane, hexane, heptane, all the way up to decane here. And what I'm trying to show you is how the boiling points increase as the chain length increases. So what you're looking at here are these numbers in the middle. So you've got CH3 on each end and then 3 CH2s in between, then 4, then 5, then 6, then 7, then 8. So as you can see, we increase the chain length, and what happens to the boiling points? They go up too. Anybody have any questions so far? Now, when you look at tetramethyl butane, this one on the bottom here, there are a total of 8 carbons in there. So you would expect that it would be closer to octane, which has a line structure but looks like this. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. So that's octane. That's a straight chain compound, and it boils at 126 degrees Celsius. Now, the tetramethyl butane looks like this. So I'll just call that TMB. And it boils at 106 degrees Celsius. So this one here is a straight chain. I would consider this tetramethyl butane to be branched. In other words, it's got a straight chain of carbons, but then it's got carbons coming off that straight chain. And even though it has the same number of carbons as octane, because of its shape, it doesn't have as high a boiling point because we can't get as much surface contact going here as we can in the straight chain. Does anybody have any questions about this example? Okay. Let me talk a little bit more about hydrogen bonding. I really quite like this little graphic here that they have. Let me see, I'm just going to try and enlarge it a little bit. There we go. All right, what I want you to do is look at this and imagine what we're talking about here with regard to each of these groups. So this is group 4, carbon, silicon, germanium, tin. So that's on the periodic table. This is group 5, the green one. You got nitrogen, phosphorus, arsenic, and antimony. And then group 6, you've got oxygen, sulfur, selenium, tellurium. And then group 7, you've got fluorine, chlorine, bromine, and iodine. So these represent groups 4, 5, 6, and 7 on the periodic table. Here's what I want you to see first of all with group 4. In group 4, we start out at CH4, and you can see that the molecular weight is low here for each one, and the boiling point is quite low. It's like minus 175 degrees or something like that for CH4. And then as we go down the group, we go down to silicon, which is bigger, germanium, which is bigger, tin, which is even bigger still. You see this progression of the boiling points going up. So let me pull up a periodic table here so you can see what I'm talking about, just in case you had forgotten. So we have group 4 here for carbon. Okay, silicon, carbon, silicon, germanium, tin. Group 5 for nitrogen, phosphorus, arsenic, antimony. Group 6, oxygen, sulfur, selenium, tellurium. And then group 7, fluorine, chlorine, bromine, and iodine. So you can see for the carbon group, this is kind of what we would expect. But if you look at groups 5, 6, and 7, you'll notice that for H2O, HF, and NH3, the boiling points are a whole lot higher than we might expect them to be. Now, when we're looking at NH3, I would have expected that NH3, if it was following the same trend as the carbon here, would have been around minus 130, would have been around here. It isn't. It's at like minus 33. It's so much higher than it should be. Same with the HF, it should be down here about minus 100. The H2O should be here about minus 80 or something like that. So what I'm saying here is that these three here are special. And the reason that their boiling points are so much higher is because they're all subject to that very special force I was considering earlier to be called hydrogen bonding, OH, NH, and FH. So that is the reason that these boil so much higher than we'd expect them to boil. All right, so how do you feel about that explanation of hydrogen bonding and why it's special? 5, 4, 3, 2, 1. Okay. Does anybody have any questions?
Isn't the first one or the fifth one, 5, 6, 7, also hydrogen bonded too?
Which ones? The CH4?
Yeah.
No, because carbon's not electronegative enough to engage in hydrogen bonding.
So that's why. All right,
Yeah,
thank you.
So it's just O, N, and F specifically to hydrogen. Those are the only ones that engage in this kind of force.
Okay, thank you.
All right, so let's look at, let me look at some examples here. Let's see. Okay, let's go to the Intermolecular Forces folder here. Okay, let's enlarge this a bit. Okay, so let me go through some examples here and how you can interpret what's going on. Initially, this is going to be hard, but you'll see it gets easier as we go. So let's look at number 1 here. And what I want you to be able to do is to be able to just look at these compounds and within 2 seconds, be able to tell which intermolecular force is the one that we're dealing with. So when we're looking at number 1, looking at the first compound here, I'd want you to see that that is van der Waal. And the reason you would know that is because it's all strictly lines. So it's all C's and H's. The second one, I would want you to see as being hydrogen bonding because it has the OH here. Now, let me point out something with this compound that has the OH. It also has van der Waal. It also has dipole dipole. because it's got the CO bond here as well. But all of those forces are overtaken by the massiveness of the hydrogen bond. And that's the one that you consider to be the intermolecular force at work in this particular example. The question here is asking which one has the higher boiling point. Because we have the strength, the relative strength as being hydrogen bonding is better than dipole-dipole is better than van der Waal, I know that the one with the hydrogen bonding is going to have a higher boiling point than the one with the van der Waal. Does anybody have any questions about this so far? Okay. Let me see how, well, I'm going to see what's your understanding of question 1 and my explanation. How do you feel about my explanation of question 1? 5, okay. All right, any questions? Let's look at the second question. I think you'll pick it up as you go. We've got two compounds here. They're both actually van der Waal, as you can see. Can anybody tell me the difference between them? It's a little bit subtle. What's the difference?
One's a straight chain, one's a branch.
Yeah, one's straight and one's a branch. Which one's the branch, Coden?
The one on the right.
That's right. Yeah, see, this one is the branch one because it's got the carbon coming off here. The question is which one has the lower boiling point? Well, the thing with the straight chain versus the branch chain is the one with the lower boiling point will be the one that has less surface contact. That'll be the one with the branch chain. So the answer is going to be this one, the one on the right for lower boiling point. Does anybody have any questions about that? All right, question 3. So out of these two, this one is van der Waal and this one here is dipole-dipole. Now the mistake that people sometimes make here is that, we've just looked at this one which has the branch on it. They look at the chlorine here and they say, oh, isn't that branched as well? No, it isn't. Can anybody tell me the distinction between these two and why this one is, this one up here is considered branched, but this one is not? It's a little bit subtle. What's the difference? Does anybody know why this one's branched, but this one isn't?
The attached molecule?
The attached molecule. Sort of.
Because the first one's attached to a CH.
A C, yeah, it's a C. That's right. See, what makes something branched is carbons coming off the main chain. I'll say that again. What makes something branched is when you've got carbons coming off the main chain. When you've got other things coming off the chain that aren't carbon, that is not considered branched. Does anybody have any questions about this?
So would it be considered van der Waal?
Well, no, this one here is considered van der Waal on the left, yes.
Right.
But the one on the right is considered to be dipole-dipole because it's got this CX bond where the X is a non-metal. So X can be anything but C or H, and that would make it dipole-dipole.
All right.
So dipole-dipole is better than van der Waal, which means the higher boiling point will be the one that's on the right-hand side.
Is branch considered dipole-dipole as well?
No. No, branching is just, when you've got branching, there's always going to be identical intermolecular forces between the two.
Right. Okay.
All right. Any other questions?
Sorry, Professor, maybe I'm just understanding it wrong, but you were mentioning C's branching off, carbons branching off, but in dipole-dipole, isn't it a carbon-chlorine bond in this case?
Yeah, but it's not a branch because the carbon chain itself is straight. When I'm talking about branching, I'm only talking about what's going on with the carbons. That's it.
Okay, thank you.
All right. Any other questions? All right, let's look at number 4. We have a CBr bond, so that's dipole-dipole, and we have an OH bond. That one is going to be hydrogen bonding. So the one with the lower boiling point will be the dipole-dipole. Any questions? Okay, number 5. We got this compound here, which is van der Waal. We got this one here, which is also van der Waal, right? Because they're all C's natures. But this one on the left is branchier than the one on the right. So this, the one with the higher boiling point will be the one that isn't as branched. So it'll be the first one. Any questions? Okay. Let's see how you're feeling about this so far. I'm actually not expecting everybody to be completely on board at this point. How do you feel? How do you feel so far about this topic? It's okay if you don't. Honestly, I'm just, just sort of getting a gauge on where you're at here. 5, 4, 3, 2, 1. I actually feel pretty good about this so far. 11 and 7. I think that's good. But don't panic if you're in the 7. All right, because we can still we're still going to do examples here and get you to the point where you're much closer to understanding what's going on. Okay, does anybody have any questions at this point? All right, let me also now relate this to solubility. Now, what we know about solubility is that like dissolves like. And then we introduce what happens when we've got hydrogen bonding versus van der Waal solvents. So just to remind you about solutions, a solution consists of 2 parts. We have a solvent, and then we also have a solute. So the solute is being dissolved in the solvent, and what that leads to, once it's dissolved, is it leads to a solution, which is considered to be both the solvent and the solute. So what we're talking about here is the kind of solvent that we're discussing. So an example here with a hydrogen bonding solvent would be water. Water is a hydrogen bonding solvent. So H bond, H2O, as you can see all these OH bonds there. And a van der Waal solvent might be, say, C6H14 or hexane, which is all carbons and hydrogens. So those are the solvents we're sort of going to talk about. So what I'm saying here is that for an H bond solvent, the highest solubility is going to be hydrogen bonding, then dipole-dipole, and then van der Waal. So we're talking about the solute here, what's being dissolved in it. So for example, if you took a hydrogen bonding solvent like water and you added sugar, sugar has lots of OHs on it, has lots of hydrogen bonds, so you'd expect it to be highly soluble. If you took water and then added oil, which is van der Waal, then you don't expect it to be very soluble, and it doesn't oil. Oil floats on water. However, if you take a van der Waal solvent, the highest solubility will be something that's van der Waal. So an example of that, has anybody ever messed with a 2-stroke engine? Anybody ever done anything with 2-stroke engines?
Yeah.
Who's that? Coden? Okay. So Coden, tell me what kind of fuel mix you have to use for a 2-stroke engine.
It's oil and gas.
It's oil and gas. Why is that?
Because it doesn't create its own lubricant.
Right, it doesn't have a sump, right? Just like a regular internal combustion engine, a 4-stroke will have a sump. It has a place that the oil can sit. But 2-stroke doesn't. 2-stroke has is a situation where where oil can't sit and lubricate the piston. So what that means is you need a mix. You need a mix of oil and gasoline, and that is actually a soluble mixture because they're both van der Waal. If oil is the solute and gasoline is the solvent here, and van der Waal is going to be the most soluble thing in a Van der Waal solvent. Obviously, if we use water, we put water in with the gasoline, but that's not going to do so great. We know that those are not going to be soluble in each other. Does anybody have any questions? All right, so I'm going to add that to the summary over here, and we're going to look at for different solvents. So for H bond, which is water, we know it's going to be H bond is better than dipole dipole is better than Van der Waal, and this is for solutes. And for the solvent that is Van der Waal, then it's going to be Van der Waal is greater than dipole dipole is going to be greater than H bond. And again, these are solutes. All right, does anybody have any questions? Okay, let's look at, here we go. No, I'm looking for that. Nope, nope, there we go. So for something like number 6 here, we're looking for the greatest solubility in water. Now water is a hydrogen bonding solvent because it's got all OHs. So we look at these, we've got Van der Waal on the left, we've got hydrogen bonding on the right. The one that's going to have the greatest solubility will be the hydrogen bonding, the one on the left. Does anybody have any questions? This one here, lesser solubility in C6H14. C6H14 is a Van der Waal because it's all carbon and hydrogen. The one on the left is Van der Waal. The one on the right is hydrogen bonding. The one that will be least soluble will again be the hydrogen bonding one. Does anybody have any questions about this? Number 8, lesser solubility in C6H14. Actually, if you look at this is actually C6H14. You expect C6H14 to be soluble in itself, but you don't have to worry about that. But this is Van der Waal. This one is dipole dipole. The one that will be least soluble will be the dipole dipole. Again, C6H14 is a Van der Waal solvent. Number 9, greater solubility in C6H14. C6H14 is Van der Waal. Dipole dipole for the one with the bromine. Hydrogen bonding for the one with the OH. Now, if you look at the solvents here for the Van der Waal is greater than dipole dipole, is greater than hydrogen bonding. So since the dipole dipole is greater than the hydrogen bonding, the answer will be the one with the BR, which is the dipole dipole. Does anybody have any questions? Okay. How's your understanding so far with the solubilities? How are you feeling about solubilities? 5, 4, 3, 2, 1. Okay. Most people are feeling pretty good about it. I'm not leaving the other ones behind. I'm just, if anybody has any questions, please ask. All right, let's take a look at some examples on the test here. And we're starting here at intermolecular forces. So which of these compounds has the lower boiling point? So I look at the top one, I see that that is hydrogen bonding. I look at the bottom one, I see that that's Van der Waal. So the answer would be that one, the Van der Waal one. Does anybody have any questions? Out of these two, which one has the lower boiling point? Well, they're both Van der Waal because they're all carbon and hydrogens, but this one's branched and this one's straight chain. So the one with the lower boiling point will be the branched one. Any questions? Which compound has the highest solubility in water? Well, we look at the intermolecular forces here. This one has an NH. Now, NH, if you look, is hydrogen bonding, right? It's a bit tricky. NH is hydrogen bonding. This one here doesn't have an OH, it just has an O, which makes it dipole-dipole. So hydrogen bonding versus dipole-dipole. The one with the hydrogen bonding will be the highest solubility in water, which is also hydrogen bonding. So that would be the answer. Any questions about that one? I'm trying to get you just to look at the molecules and just be able to tell, in an instant, what intermolecular force you're dealing with. If you can get to that point, then I'm happy as Larry. That's all I really wanted. Which compound has the lowest solubility in water? Well, again, NH, that's hydrogen bonding. And this one here is dipole-dipole. The one with the lowest solubility will be the dipole-dipole, will be this one here. Does anybody have any questions? All right. Okay, we're going to leave it there for today. If anybody wants to hang around and ask me any questions, they're certainly welcome to. And as for the rest of you, I will see you all next Monday.
See you Monday.
Thanks, Professor. Have a good day.
Thank you. See you all.